All right, everybody, welcome to our second calculus unit. This unit is about differentiation. We're going to talk about the definition of it and some basic rules of it later on in this unit. But to start today, we're just going to talk about defining the average rate of change versus the instantaneous rate of change at a point. Let's start today by talking about a tangent line. What is a tangent line? People like to say a tangent line only touches a curve at exactly one point. While that's kind of true, it's not always true. You can see in the first picture here, here's a tangent line. And yes, that's only going to touch the curve at that point. Same thing in the second picture here. That tangent line is only going to touch that curve at that point. But here's a picture here. This is a tangent line. But you can see as it extends, it will touch the curve again. Really, it's just a line that kind of touches a curve at a point between a certain interval. So, between here and here, that's a tangent line, okay? A secant line is a line that intersects the curve at least twice. So technically, if you drew this whole line in, this would be called a secant line. But if we focus on just this part, now it's called a tangent line at that point. Let's talk about a couple misconceptions of tangent lines. The first one here is a line that is tangent to a curve if it crosses a curve at exactly one point. Well, here's a line that crosses the curve at exactly one point, right? But that is not what is called a tangent line, okay? Another misconception here is a tangent line to a curve must cross the curve only once. This is a tangent line, but it's a tangent to the point P. But you can see it goes through the curve more than one time. A third misconception here is a line is tangent to a curve if the line touches a curve at one point but does not cross the curve. This is not a tangent line, okay? Although our line L touches a curve at point P, it is not considered to be a tangent line. And finally, the fourth misconception, a tangent line to a curve is a line that just grazes the curve at a point but does not cross the curve. That's not necessarily true. This is called a tangent line right here. It would be called a horizontal tangent line in this example. Line L is tangent to the curve at C at point P, but it does cross the curve at point P as well. So it's really hard to actually put a formal definition on what a tangent line is. It's more about visualizing it and seeing, does it just touch the curve at a specific point, okay? So in the first week of school, we talked about the tangent line problem and how basically the tangent line problem sums up the first half of calculus AB. So we're going to start with a graph y equals f of x, any graph. Here we have a graph of f of x, okay? We're going to pick a random point and we're going to call it c comma f of c. So that point would be right there. Then we're going to choose another point in the curve that has a horizontal distance of delta x units to the right of our initial value. So what does that mean? How about right over here? Okay. And we're saying the horizontal distance between those 2 points is called delta x. Some people call it delta x, some people call it h. We can call it whatever we want. It really doesn't matter. But delta x is a good name for it because delta means the change in. So we're talking about the change in x. All right, so that new point, we're going to call that new point x comma f of x. If we connect those points with a line, that would be called a secant line. And the question is asking, what is the slope of the secant line joining those points? All right, the slope is just y2 minus y1 over x2 minus x1. All right, step 2 here. Let's take that second value and move it a little bit closer to our c comma f of c. So how about right there? And let's connect those 2 points. And again, now we're going to call this x comma f of x, and the distance between them is delta x. Is there still a secant line? Yes, there is. It's still a secant line. It still does cross that curve multiple times. How would we calculate its slope? The same way. It would be the same slope. Step 3, now let's take that first point, and once again, let's move our second value so close that it's almost touching C. So close that it's pretty much right on top of C, f of C. And if we draw a line in now, do we still see a secant line? Well, technically, yes, it's still a secant line because it's still going through 2 points, even though we probably don't see it. We probably see a tangent line, but there is still technically a secant line there. How could we perceive the slope now using a very important concept from Unit 1? Well, remember Unit 1 was talking about limits, right? So if we take the slope of the secant line, but if we take the limit as our second x value, x, approaches our first x value, c, that's how the slope is going to be changing as we get closer and closer and closer to merging those points together. So we say this is the slope of our tangent line. Okay, and up here, the first two, this is our slope of our secant line. This is a very important concept for the first half of Calculus AB. The definition of a tangent line with slope m. All right, if f is defined in an open interval containing c, if the limit, so again, this is our slope of a tangent line, right, exists, then the line passing through the point c comma f of c with slope m is a tangent line to the graph of f at the point c comma f of c. What does that mean? Just like when you did in Algebra 1, if you have a point and a slope, you have a line. If you use this point and this slope, then you've created what's called the tangent line to the graph of f at the point c comma f of c. So let's take a look at an example here. The first one just says to find the slope of the graph of that function at the value x equals 1. And you might be thinking right now, that's really easy. I know the slope of that graph. The slope of that graph is always the same. It's 2. And you're right, it is 2. All right, but we're going to take a little journey here, a little adventure into proving it to be 2 using our newfound limit definition. Okay? So what we're going to write here is something kind of new for us as well. We're going to write f prime of 1. What does that mean? Well, for right now, let's just call it, that means the slope of f at 1. Okay, it means something else that we'll talk about later on. But right now, it means the slope of the function f at 1. All right, so we're going to take the limit as x approaches 1 of f of x minus f of 1 over x minus 1. All right, and as of right now, we cannot use direct substitution. It's not possible because we would get 0 over 0. But that means we just need to do a little bit of work. Limit as x approaches 1 of 2x minus 3 minus 2 minus 3. So that would be minus negative 1 over x minus 1. That would be limit as x approaches 1 of 2x minus 2 over x minus 1. We still can't directly substitute, but now we can factor in the numerator a 2. And then canceling the x minus 1s, we get 2. There's nowhere even to put the 1 in, but that's okay. Our answer that we learned is a constant. which is 2. All right, so we would write f prime of 1 is equal to 2. What does that mean? That means the slope of function f at x equals 1 is 2. All right, what if it's not linear? Well, now we don't just know the slope of this graph because it's changing. So that's where this definition comes into play. All right, so if we want to write f prime of 1 equals limit as x approaches 1. By the way, it's not always 1. I just happen to pick 1 for both of these examples, but it could be anything. Of f of x minus f of 1 over x minus 1. And that gives me limit as x approaches 1 of x squared plus 1 minus 1 plus 1, which is 2, over x minus 1, which is limit as x approaches 1 of x squared minus 1 over x minus 1. And we're almost to a point where we can put 1 in, but not yet. If we factor the numerator, we get x plus 1, x minus 1 over x minus 1. And now if we cancel, we're left with that. And if we put 1 in, we get 2 back. So what does that mean? For this problem, the derivative, which is a word that we're going to talk about again later on, which is the slope of f at 1, is equal to 2. So on this function, the slope of that function when x is equal to 1 would be 2. All right. The limit equation we've been working with so frequently used, a special notation is used. Okay, and I've already been using it with you, but now we'll actually know what it means here. It's f prime of c. You'd read that f prime of c is used to denote the slope of a tangent line to a function f of x at x equals c. All right, so you can see you're kind of cut off here. But f prime of c is equal to the limit as x approaches c of f of x minus f of c over x minus c. And we call f prime of x the derivative of f of x. So it's called the derivative of f of x. That's a very important word in our calculus journey. All right, so we're going to finish today with one more example here. If f is a function for which the limit as x approaches negative 2 of f of x minus f of negative 2 over x plus 2 is equal to 0, which of the following statements must be true? Okay. So part A says x is equal to negative 2 is a vertical asymptote of the graph. And you might think of that, oh, that looks like that's the answer because you put negative 2 and you're going to get 0 in the denominator. But this is not the actual function. Only this is the function. All right, we don't even know what the function is. Okay. Also, the fact that this is telling us the limit actually exists at negative 2 tells us there's no way this is true. Okay, because the limit exists, we cannot have a vertical asymptote at x equals negative 2. Because if there was a vertical asymptote, then the limit would not exist. Part B, the function f is continuous at x equals 2. Well, that's talking about x equals 2. We don't know anything about x equals 2. This is just talking about x equals negative 2. So could that be true? Could B be true? It could, but we have no idea whether it is or it isn't. All right? Let's skip C for now. Let's talk about D. F is not defined at x equals negative 2. Well, that's definitely not true. Because this is saying, remember, this is the derivative at negative 2. This is saying the derivative does exist. In order for the derivative to exist, the function must be defined. So D cannot be true either. Which brings us to C. The derivative of f at x equals negative 2 exists. This is the derivative of f at x equals negative 2. And we're being told it exists. And not only does it exist, but the answer is 0. But that doesn't matter. All that matters is that it does exist. So our answer for this problem would be C. All right, that's it for our starting into Unit 2. Next time we'll take a look at a little bit deeper dive into what a derivative is and an average rate of change and an instantaneous rate of change and the difference between those. Thanks for checking in, and we will see you next time.